How can you understand wave-particle duality without complex math? Imagine trying to understand a magic trick where something can be two things at once. That's what wave-particle duality is in the world of tiny particles like electrons and photons. It's a strange idea, but it's at the heart of quantum mechanics. Instead of jumping into complicated formulas, let's look at some simple ideas that make this concept easier to grasp. First, think about everyday objects. A particle is like a tiny ball or a grain of sand. It has a specific place where it is. A wave, on the other hand, is like ripples on a pond or the sound waves you hear. Waves spread out over space and can interfere with each other, creating patterns of high and low points. Now, picture shining light or shooting electrons at a barrier with two narrow slits. If these tiny objects were just particles, you'd expect to see two bright spots behind the slits where they land. But what actually happens is more surprising. Instead of just two spots, a pattern of bright and dark bands appears on the screen behind. This pattern is called an interference pattern and is a clear sign of wave behavior. Even if you send one electron at a time, over time, the same pattern still forms. That means each electron acts like a wave passing through both slits at once and interfering with itself. It's like a single wave splitting and then recombining, creating those bright and dark bands. This experiment shows that particles can behave like waves, even though they arrive as tiny, localized impacts. It's a key piece of evidence for wave-particle duality. But here's the twist. You can observe wave behavior or particle behavior depending on how you set up the experiment. If you look for particles, you see particles. If you look for waves, you see waves. They are two sides of the same coin. In quantum mechanics, the wave behavior of a particle is described by what's called a wave function. Think of it as a cloud of possibilities where the particle might be. It doesn't tell you exactly where the particle is but gives the chances of finding it in different places. This idea helps explain why particles seem to spread out and why they act differently depending on how you observe them. Another important concept is the Heisenberg uncertainty principle. It says there's a limit to how precisely you can know both the position and the speed of a particle at the same time. Because waves are spread out, trying to pinpoint an exact location makes it harder to know how fast it's moving, and vice versa. This uncertainty is a direct result of the wave nature of particles. Understanding wave-particle duality is essential for many modern technologies. Quantum computers, secure communication systems, and advanced sensors all relying on the fact that tiny particles can behave both as particles and as waves. By thinking about experiments like the double slit and imagining particles as clouds of possibilities, you can get a good grasp of this strange but fundamental part of the quantum world without needing complicated math. It's a fascinating way to see how the universe at its smallest scales works in ways that challenge our everyday experience.